Hello, welcome back to Larry's Classroom. We're going to continue the discussion of Ohm's law, power, resistors, etc. If we have a resistor here, this is a 100 ohm resistor, and we have a 10 volt supply, we will have, well, the current I equals the resistance equal the voltage divided by the resistance, which is 10 volts divided by 100 ohms here, which will give us 1/10 of an amp, which I have written up here. Now power, we have a formula for power. Power equals voltage times current. So we take this voltage, power equals voltage times current. So power will equal, in this case, 10 volts times 1/10 of an amp, which will be 1 watt. So we have a power source pushing a current, causing a current to flow through this resistor. This power of 1 watt will be consumed in this resistor as heat. It will turn to heat and dissipate into the atmosphere. Now we've done this as a 1 watt situation, and what happens if you have 1 watt of heat dissipated from that resistor, or 1 watt of heat created from the current flow, 1 watt for 1 second will be amount of heat equal to 0.24 calories. The first thing I want to talk about when it comes to calories, when you think of this kind of calories, notice we have a small c, lowercase c. This is not the same kind of calories you see published on food labels and such. In food, they use what's called a kilocalorie. Kilocalorie. And you'll see that written as CAL, a large uppercase. So one food calorie is 1,000 heat calories. And of course we've talked about already energy in the form of joules. So we're going to correlate a joule to a calorie. 1 joule or 1 calorie, excuse me, 1 calorie of heat is equal to 4.186 joules of energy. So calorie is actually a little bit bigger unit than a joule. And as we talked about a few minutes ago, when we're talking about food calories, which we're not going to talk about that too long, but I want you to realize that the calories of heat and the calories of food are not the same. That's a kilocalorie, or that's written as capital C. And basically, being a kilocalorie that's equal to 1,000 of the little calories that we call for heat. That also tells you that there'd be 4,186 joules per kilocalorie. So 1 calorie of the labeled on your food labels is 4,186 joules. 1 calorie of heat is equivalent to 4.186 joules. I'll tell you one more thing about a calorie and then we'll move on here. Calorie is the amount of energy to raise 1 gram of water, which should have a volume of 1 cc, by 1 degree Celsius. So to raise 1 gram or 1 cc of water, 1 degree Celsius takes 1 of the small calories. But by the same token, we talked about the food size calorie. That's the amount of heat that's required to raise 1,000 grams, 1 degree Celsius. Let's see, I'm going to take this grams off of here because I'm not 100% sure that a gram of water weighs a cc. I'd have to look that up. But 1 cc of water, which is a little cube the size of a centimeter on each side, little tiny block, a little bit smaller than probably a typical dice. If you have enough heat to raise that 1 degree Celsius, that's 1 calorie. But being the kilocalorie is 1,000 times as big, it would take 1 kilocalorie to raise 1,000 grams or 1,000 cc's of water by 1 degree Celsius. But 1,000 cc's of water is also what we call 1 liter. But we're not going to worry too much about kilocalories and food calories, but I wanted you to know there's a difference in case somebody tells you so or argues with you about something. So back to the 1 watt that we're drawing here, because we have a tenth of an amp times 10 volts. We have 1 watt of power being consumed. If we do that for 1 second, we will produce enough heat, which will be dissipated out of this resistor. We use to warm the resistor out, and then it'll escape into air to be equal to 0.24 calories of heat. Now, since power in a resistor is dissipated as heat, it's convenient to have power formulas that are rated to resistance. We started out with power equals volts times amps. Voltage in V and current in amps. But we also have, this is a power formula, from the Ohm's law. We know that V is equal to current times resistance. A lot of times we'll call that IR. So we're going to take this here formula. This is an equation. I've told you before that the equal sign, that each side is the same thing. Voltage and IR are the same thing. So we can replace the V over here with IR. So we'll say that power equals IR times I. Now, we're multiplying I times IR, but you're probably aware that I times I is equal to I squared. Or if we had 5 I's, I times I times I times I times I is equal to I to the 5th. So this exponent, when you look into the variable, just tells you how many variables you multiplied times itself to get this number. So we can take this I and replace it with I squared. I squared times R. So power is equal to I squared times R. You'll often hear say power equal I squared R, which basically that's where we got that thing, I squared times R. So we've now expressed our power in relation to resistance and current. I'm going to write that up here. Power equals I to the second power, I squared R. I'm just going to put the two variables together. When you put two variables like that together, you do not need to put a multiplication sign. It's implied. And of course, when you were to solve this, we haven't talked too much about the order of operations, but I will tell you that exponents, like right here, comes before multiplication. So if I gave you I equal to 2 and R equal to 3, we would rewrite this as 2 amps squared times 3 ohms. Well, we would do this exponent first, which would be 4 times 3 would be 12 watts. And we will discuss order of operations a little more at some point, but right now I don't want to get too involved in that particular thing, but we do the exponents for the rest of the multiplication. Now in this case, if we wrote them out, they'd all be multiplication, so it really wouldn't matter, but when you get numbers in there, it's a little easier to do that. So now we've expressed our power in the forms of current and voltage. I'm going to write that here. Our current resistance. Those are the terms that we express our power in. But we have another way of expressing power in terms of resistance and voltage. We had power equal to voltage times current. Now we know that current is equal to voltage divided by resistance. So we're going to use substitution here, and we're going to substitute VR for I here. Power equals voltage times voltage over resistance. Now anytime you have a variable, V is equal to V over 1. Doesn't change it. There's an implied denominator of 1, so we're going to rewrite it that way. V over 1 times V over R. Now here we have two fractions. We multiply fractions by multiplying everything in the top, which we call the numerator, times everything in the bottom, which we call the denominator. So we have power equals V times V, or we'll just write that as V squared, over 1 times R, we'll just write that as R. So now we have another power formula that's based on the resistance. So power equals V squared over R. So we've, in this case, we express our power in terms of voltage and resistance. And these can be quite handy when you're talking about resistors, because the heat, which is power, or which comes from power, 1 watt per 1 second gives you the 0.24 joules we talked about. So the heat is actually power times the time. But we express power, and being the energy is dissipated in the resistor in terms of heat, it is handy to have power formulas that are expressed with resistance. So here we've got current resistance and voltage and resistance. That gives us a useful, I mean all these are useful, but this we might be finding to be quite useful. Now we're gonna draw a little circuit here. We're gonna talk about it. So we actually have up here, I'm gonna put this one here, power equals voltage times current. So here it's expressed in voltage and current. So we have three power formulas here. One expressing voltage and current, one expressing the power in current and resistance, and one expressing the power in voltage and resistance. I'm going to draw a little circuit here. 10 volts. We're going to draw a resistor over here. Resistor over here, this is going to be a 5 ohm resistor. Let's calculate the current. We remember Ohm's law that said current equals voltage divided by resistance. So what we have here is 10 volts, and we have 5 ohms, which is 2 amps. So we have a current of 2 amps, and we're expressing this as electron flow, which electrons flow from negative to positive. So I put an arrow to indicate the electron flow, the electron current flow direction. Now we're going to calculate the wattage in this particular circuit. And the first one, we have power. Let's do this down here. Power equals voltage times current. I sometimes put the dot to indicate multiply. Sometimes I put a little X, and other times nothing. When you put variables together, the multiply is implied. So we're going to 10 volts from our circuit, and we're going to multiply that times the 2 amps that we just calculated. And 2 times 10 is 20 watts. So this battery is supplying 20 watts of power, which is being converted to heat by this resistor and causing the resistor to warm up and causing the heat to eventually enter the atmosphere. We're going to use our other power formula, I squared R, which we had derived here by substituting. We substituted V. What do we substitute? We replaced the V with IR. Yeah. So I is 2, so we're going to go 2, and we're going to put the little exponent up there to indicate we're squaring that. R is 5. We're going to put a dot to indicate multiply here. So 2 squared, 2 times 2 is 4, times the 5 ohms, and we end up still with 20 watts. Now we're going to use our other formula, and here that we derived a little bit ago. In this case, we substituted V over R into this to get a power formula in terms of volts and resistance. So we're going to write that down here. Power equals voltage squared over resistance. So the voltage is 10 volts. And we're going to square that. Well, we'll put the little exponent 2 up here to indicate that we're squaring that. The resistance is 5 ohms. So 10 times 10, 10 squared is 100, divided by 5, because a fraction is basically a division indicator. That equals 20 watts. So what we see here is we have calculated power using 3 different formulas that we derived, and we have shown that we do come up with the same value in each case. Now, in some cases it's good to have the heat dissipated. For example, I'm going to erase all of this for right now. If we had a heater like a toaster, we would like having the heat to be the power being converted for heat, because we want that heat to cook the sides of our breads to make it into toast. A heater in your home, same thing. So in not every case is heat, power being converted to heat, a waste. It's actually desired. In the case of a light bulb, we'll draw a little light bulb here. We'll put 120 volts on it. We won't worry about the value of it. The symbol for a light bulb, a little globe with a filament in there. I will say this is a 60 watt light bulb. And 60 watts, we basically have half of an amp flowing here. Power equals volts times amp, 1/2 times 120, 60 watts. What that energy is doing, the filament, this we're talking about an incandescent bulb. We do a lot of things with LEDs and stuff nowadays for more efficiency, but that's essentially a resistor. So this 60 watts of energy here is being used to heat that filament. The hot filament glows and gives off light. So we have here a light bulb, gives off light by heating the filament to a white hot temperature, and that's how we get light out of power with an incandescent lamp. And even though the heat energy is not what you're after, it is useful to it because it makes the filament glow, which is something we desired. Now we're gonna do an example here. We're gonna put 100 volts. And we're going to put 50 ohms here. I equals V over R, so we have 100 over 50, so that's 2 amps. So we'll put 2 amps here for our for current. We want to figure how much power is being dissipated in this resistor. We know that power, because we solved that a little bit ago, I'll write it back up here. Power equals I squared R. Power equals VI. And we had power was equal to V squared over R. So we got this resistor giving off heat. I'm going to draw some little lines to indicate the heat is coming off that resistor into the air around the resistor. Anyway, so we have the 2 amps, the 100 volts. So we're going to use this formula. Power equals I squared R. I squared R. So we're going to put the 2 amps, 2 squared, times 50. So we have, this is 4 times 50. So this gives us 200 watts. And we're going to use the same example with the same voltage, and we're going to show that we've already calculated the voltage, or calculated the current, we're given the voltage. Power equals voltage times current, V times I. Our voltage was 100 volts. Our current was 2 amps. And again, 2 times 100, 200 watts. So we've kind of looked at how power is dissipated in a resistor. We've looked at how the calorie is a form of, can be related to wattage, and wattage time, 1 watt for 1 second was 0.24 calories, yeah. And we talked about that food calories and these little heat calories that we talk about are not quite the same. Now, we're going to do one more thing we're going to talk about here. Power equals, we're going to use the VI. And we're going to transpose that, we're going to solve for I. So we're going to divide. Now this equal sign equation says that P and V times I are the same thing. So if we want to solve for another variable, the basic rule of algebra, whatever you do to this thing, you got to do this thing if you want to keep still being the same. So we're going to divide by voltage, divide by voltage. So what we have here now is the voltages cancel. So we have here that I, the current by itself, is equal to the power divided by the voltage. So we have power of 240 watts. We have voltage equal to 120 volts. And using this formula, I equals P over V, we have I equals power, 240 watts, divided by 120 volts, and that comes out to 2 amps. Now, if we have a different heater, the same wattage, still a 240 volt heater, 240 watt heater, but we'll run that heater on 12 volts rather than 120 volts, so we got 12 volts. We use the same formula. We want to solve for current. We have power over voltage. We'll substitute in our values. Power 240 watts. The voltage 12 volts. And 12 goes into 240. That ends up being 20 amps. So what we've seen here, we can get the same 240 watts using 120 volts or 12 volts. But what changes is the current. We need more current to get an equal amount of power with a lesser voltage. In this case, our voltages were 10-to-1 ratio. So when we made the voltage 1/10 as much, we needed 10 times as much current. Or if we went the other way, going from 12 volts to 120, we made the voltage 10 times as much, we need 1/10 as much current. So you can get the same current with a high voltage, or the same wattage, the same amount of power, with a high voltage and a low current, or with a low voltage and a higher current. Now we're going to do a little more work with all these power formulas. We're going to start with some of this we've already done, but we're going to summarize it. Power equals VI, voltage times current. I'm going to take the dot out. I'm just going to put them right next to each other. VI, voltage times current. Now we're going to do like we did before. We're going to substitute in. We want to get rid of the voltage, and we know from Ohm's law that voltage equals current divided by current times resistance. Current times resistance. So we're going to substitute in here into this power equals voltage times current. We're going to substitute the IR in for voltage. Power equals IR times I. Push the i's together, put the exponent. Power equals I squared R. So to write that power formula up here, power equals I squared R. And we did this already, but we're going to kind of work out some completeness. Now we also know from Ohm's law that current equals voltage divided by resistance. We're going to use the same power formula that we started with. We're going to substitute the V over R, voltage divided by resistance, in for the I. So we say power equals voltage times voltage over resistance. So we replace the I, the current, with the Ohm's law formula for current, voltage over resistance. Now we multiply this out, we end up with power equals V squared. The V times V makes V squared over R. So now we have our third power formula, which we did this a little bit ago. Power equals voltage squared over resistance. So we have three different power formulas, and if we do the algebra and solve this one for I, we end up with I equals power over voltage. And if we solve it for voltage, we have voltage equals power over current. But we're going to solve each of these for the three different variables. We're going to solve this one for resistance. We have resistance equals power divided by I squared. And what we did is we just divided both sides by the I squared to get to that. We also want to solve that particular equation for current. So this is going to be a two-step process, or a couple steps. We're going to power equals I squared R. We want to solve it for I, so we're going to divide both sides by R. So now we have power over R. Power over resistance is equal to I squared. I'm going to change the order of this equation. I squared equals power over resistance. Now, as I said, we do the same thing to both sides of the equation, and that will keep it equal. We have I squared. We want to get just I, so the square root of I squared is equal to I. So what do we want to do? We want to take the square root of both sides. So we're going to put the square root of I squared is equal to the square root of power over resistance. We've taken this thing, square root of I squared, taken this fraction, square root of that fraction. Now we know that the square root of I squared is simply I, so we have here that I equals the square root of power over resistance. So we've solved this particular second form of the power equation, which uses current and resistance for current. So we have that current equals the square root of the fraction power over resistance. Now we're going to solve this particular one for R and then for V. Solve it for R. We'll basically multiply both sides times R and divide both sides by P, and we end up with R is equal to the voltage squared over the power. We want to solve this same thing for voltage. So I'm going to do that down here. Just to power equals voltage squared over resistance. So we're going to multiply both sides times R. Times R. These R's cancel. This just becomes RP. Power times resistance equals voltage squared. But we're trying to solve for voltage, and just like we did before, the square root of V squared is equal to V, the square root of voltage squared is equal to voltage. So we're going to take the square root of both sides just like we did before. Square root of P over R is equal to the square root of the voltage squared. Like always, we do the same things to both sides of the equation, and it will remain a true equation. And now we're going to replace this with V, square root of power times resistance is equal to V. I'm going to change the order because that was our goal to solve for V. Say V is equal to the square root of the power times the resistance. And now we're going to put that up here. The voltage equal to the square root of power over resistance. So now we got a pretty full set of the power formulas. We started with the original one. Power was voltage times current, voltage times current. We solved it for current, we solved for voltage. Then we did the substitution, got this second power formula, and we solved it for resistance, and we solved it for current. We did a different substitution to get the current out of this thing, and these were Ohm's law substitutions to get to these second two columns. And then we solved this power formula for resistance. We got resistance equal voltage squared divided by power. We solved for voltage. We got voltage equal to square root of, well, we got the wrong thing here. This is P times R. Voltage equals PR. Yeah, square root of PR. Copied it down wrong, I guess. Anyway, so now we got a pretty full set of power formulas. We can find power if we know current and voltage. We can find power if we know current resistance. We can find power if we know voltage and resistance. Find current if we know power and voltage. We find resistance if we know power and current. We can find resistance if we know voltage and power. We can find voltage if we know power and current. We can find current if we know power and resistance. We can find voltage if we know power and resistance. So we're going to do a few examples using these fairly complete set of formulas. Let's we got a 120 volt supply, and that is powering this is a 720 watt heating element in a toaster. In a toaster. We want to know the current. We have the voltage, we have the wattage. So we need to find a formula that solves for current using power. I'm going to give it a little gap here so you can see. We want to solve for current, we know power, and we know voltage. So we got three different current formulas. Here we can solve for current if we know power and voltage. Here we can solve for current if we know power and resistance. So I guess we got two different current solving formulas here. So we have voltage and power. So I think we're going to choose this particular formula. Current equals power divided by voltage. So let's write that down here. Power divided by voltage. and we have a power of 720 watts. We have a voltage of 120 volts. And if we divide 720 by 120, we end up with 6 amps. So let's draw a little arrow here, 6 amps. So with given the voltage and given the current, we have been able to determine the, given the voltage and given the power, we're able to determine the current. Let's suppose we want to know the resistance of this heating element. Now we could use the voltage and the current in Ohm's law and get the resistance, but let's do it with a power formula. We want to find the resistance, and we have using voltage and wattage. Okay? So we have a formula for finding the resistance with the given voltage and the given wattage. Resistance, here it is. So we'll use that formula. Resistance equals voltage squared over power. So our voltage was 120 volts, so 120 volts. And our power was 720 watts. So we want to square that, 120 squared. And if we do the arithmetic, 120 squared over 720, I'm going to grab my calculator and punch the numbers in here. $120 squared gives us 1,440. 14400, and we're going to divide that by 720. Divide that by 720. And we end up with the same. We end up with a resistance of 20 ohms. And just to double check ourselves, let's go to our Ohm's law. So here we found the resistance when given the voltage and the power, voltage and the wattage. We'll go to, and we calculated the current earlier, right here, when given the voltage and the wattage. But let's double check this real quick on our Ohm's law. Remember that resistance was equal to voltage divided by current. Using this calculated current and the given voltage, we have a voltage of 120 volts, and the calculated current was 6 amps. And when we do the math, it comes out to 20 ohms. So either approach gave us the same resistance. But it was convenient to have derived this full set of power and power formulas, because every one of them is power. Yeah, this full set of power formulas in relation to voltage and resistance and such. Made it easy for us to select the right formula to use. Now we're going to draw another circuit here. I'm going to leave these formulas up here for now because we might be using them. We've got 10 volts. And we got a 5 ohm resistor here. And we have a second branch which has 2 5 ohm resistors in it. These are parallel branches. The voltages, the voltage here, I'm going to draw the voltage here, and the voltage here, and the voltage here, a little V, is all the same because the wire that this line represents has basically zero resistance, or very close to zero, so we don't see a change in voltage from here to here. So we can analyze these two branches separately. get this stuff out of here. We can simply disconnect this particular branch, and we can analyze this particular section on its own. So we have current equals voltage divided by resistance. We have 10 volts. We have 5 ohms. So we end up with 2 amps. So we get 2 amps flowing here in this branch. Let's calculate the wattage with the original voltage and ohms given. So we want to find something that has a formula up here that has voltage and ohms, voltage and resistance, and gives power. Well, here we have it. Power equals voltage squared divided by resistance. So power equals voltage squared divided by resistance. And just look at this branch. After we disconnected that branch, we have 10 volts squared. So we have 10 squared divided by the 5 ohms, which is 100 divided by 5, which brings us again to a 20 watt. So we have 2 amps flowing for this through this particular 5 ohm resistor, but we also have this 20 watts being dissipated as heat by that 5 ohm resistor. Now let's look at the other circuit, the other branch. Let's reconnect it. And because it's a parallel branch, we can disconnect that thing and look at this one separately. Well, we have 2 5 ohm resistors, but resistors in series add. I think we've talked about this. We have 5 ohms plus 5 ohms. So basically, we have 10 ohms total, and we could even replace this with a 10 ohm resistor. But I'm just going to say resistance total equals 10 ohms. So we're going to calculate the current in this branch. Same 10 volts. Okay, that's pretty easy. Current equals voltage divided by resistance, and we had 10 volts, and we had 10 ohms, which basically was 1 amp. So we end up with 1 amp flowing through here, flowing through this branch. Let's figure out how much power is being dissipated in this branch. We're going to go back to our given 10 ohms we got by adding those two, and the 10 volts. Power equals voltage times resistance. We use the same thing. Power equals voltage squared divided by resistance. And we had a voltage of 10 volts. And we'll square that. And our total resistance was 10 ohms. So we have 100 divided by 10, or 10 watts. 10 watts. So we have 10 watts being dissipated in this branch of the circuit, and we hook it back up, we have 20 watts being dissipated by this, in this branch of the circuit, as heat in that resistor, and the 10 watts over here is heat in those 2 resistors. We have 1 amp here, 2 amp here. Our power supply is going to have to supply a total of 3 amps because it's got to supply enough current for both of the branches. What we've demonstrated here is that parallel branches, you can analyze them separately, which is what we just did by disconnecting them and such. And real quickly, remember in the 5 ohm resistor we had 2 amps and 20 watts. In the two 5 ohms in series, we had 1 amp and 10 watts. Well, note that 20 plus 10 is 30 watts. And 2 plus 1 was 3 amps. We had a 10 volt supply, and we were drawing a total of 3 amps. We'll use this little power formula here. Power equals voltage times current. So we had 10 volts, current of 3 amps. 3 amps again gives 30 watts. So we see that the power supply has to supply that full 30 watts, although only 20 watts of it was being in the single resistor, and the 10 watts was divided equally amongst the two resistors in series. But the power supply still had to supply that total amount of power. Suppose you need to choose a resistor. We've got a circuit, 100 volts. We have a current given to us of 0.1 amp, or a tenth of an amp. And we have a resistance, we call this R1, which is equal to 800 ohms. And we have another resistor. We need to pick a resistor here for R2. We need to pick a resistor which will give us the 1/10 of an amp. Well, if we look at we need a total resistance. We have from Ohm's law, resistance equal voltage divided by current. We were given a current, we're given one resistor, we're given a voltage. We need to decide what value we need for this resistor R2. First, we need to know what we need for total resistance in the circuit. So RT is going to be the given voltage of 100 volts. We're just substituting in that Ohm's law expression for resistance, divided by the given current of 1/10 of an amp. And we divide 100 by 1/10, we end up with 1,000 ohms. Now, as we talked about before, resistances in series add, so our RT, our total, the total resistance we need, is going to be equal to R1 plus R2. R2, we're trying to decide we need. We're given R1, we've calculated what RT needs to be based on the given voltage and given current. So we're going to say 1,000 ohms for our RT that we can't calculate it. It's got to be equal to R1, which is 800 ohms, plus R2, which we are currently trying to calculate the needed value for. Well, again, we have an equation. We have to find the value for R2 that makes this equation true. We know that 1,000 ohms has got to be equal to 800 ohms plus R2. So we want to get the R2 alone. So we want to get this 800 out of here. So let's subtract 800 ohms from this left side, or right side of this equation. But being we subtracted 800 ohms from the right side of the equation, we got to subtract 800 ohms from the left side to keep this equation balanced and true. So we're going to subtract 800 ohms minus 1,000 ohms minus 800 ohms leaves us with 200 ohms. And we take the 800 out of there, so we end up just left over here. The 800 ohms minus 800 ohms is 0 ohms. 0 ohms plus R2 just leaves us R2. So what we've realized, if we are given this circuit, we don't know this resistance, but we're told we need a current of a tenth of an amp at this voltage and this resistor, we have calculated that R2 has to equal 200 ohms. So we've successfully chosen our resistor based on criteria that were given. Now we're going to quickly look at, we chose a resistance. We also need to choose a wattage rating. If we put too small of a resistor, too small of a wattage rating, which is usually physically smaller, that resistor will fail. We know we're given current, we've calculated both the resistance, so we're going to use this power equals power equal current squared times resistance. So let's figure out what size of wattage we need here. We're given power, we need a resistor capable of dissipating that amount of power. Power equals I squared R, and for R1 and R2, they're both the same current, because the current in a loop is the same everywhere. Same current. So we're going to say power equals 0.1 quantity squared times the resistance, which is 800 ohms. Well, we square that 0.1, we have 0.01, which is basically 1/100th, and we're going to multiply that times 800 ohms, which leaves us with 8 watts. So we need an 800 ohm resistor here, rated to dissipate at least 8 watts. It's hard to find carbon resistors that are greater than 5 watts, so we will probably end up choosing a wire wound resistor. For R1, we're going to have an 800 ohm, and we're probably going to find, a 10 watt. Probably going to be a 10 watt. As long as it's greater, you'll be fine. If we put a 4 watt resistor in here, it will eventually overheat and probably burn open. If we put a 20 watt resistor, it can dissipate that 8 watts all day long with no problem. So we're probably going to be choosing something like a 800 ohm 10 watt wire wound resistor. And the reason it would be a wire wound is because you're probably not going to find an 8 or 10 watt carbon resistor very easily. So we're given resistance. We calculated the needed resistance to get the desired amount of current with the given amount of voltage. And we now have calculated the wattage dissipation need for the first resistor. Well, the second resistor is 200 ohms. I'm going to do this in different color just to kind of help you from So we're going to do a few calculations for R2. And we're going to use the same power equals I squared R. And this is for R2. Again, it's power equals I squared R, which is the formula that we selected from here. And we're using the power. The reason we're using the power formula is we need to know how much power this resistor has to be able to dissipate without failing. So we have same current, 0.1 amps, which is squared. We have a different resistance now. We have 200 ohms. So power equals 0.01 squared times 200 ohms. So we're going to say power equals 0.01 is still going to squared is still going to be 0.001 or 1/100th. Oh, I put an extra 0 there. 0.01 or 100th. Multiply that times 200 ohms. So we're going to need 2 watts here of dissipation capability. There will be 2 watts of power consumed here. So R2 will be a 200 ohm resistor, which we calculated earlier. It has to have at least a 2 watt dissipation rating. You could probably find a 2 watt carbon resistor, but we might choose a 5 watt to give us a little headroom. So we would probably choose a 5 watt, which we can find in the carbon resistor, and that way we have plenty of power dissipation headroom. We're not going to have an issue with that resistor burning up in normal circumstances. And you can see also that same current through them, the larger resistance dissipated more heat and needed to be physically larger to keep from burning up than the smaller resistance needed to be. I'm going to erase all this. We're going to talk about electric shock and electrical safety. You always got to have a little bit of that in an electrical circuit or electrical course. We've derived a bunch of power formulas. We've learned how to choose a resistor with given criteria, which in this case was one resistance was given, and the voltage was given, and the current that we're seeking was given. Anytime you're dealing with electricity, it's not impossible to get a shock, electric shock. Well, most of you at some point in your life probably received some kind of electric shock, and it causes you to jump away involuntarily, really. And even if the electric shock is not enough to actually injure you, it is possible when you're jumping away to bump into something sharp and be injured that way. So electric shock is certainly a thing to be concerned about. Now the human body, from hand to hand, typical resistance, hand to hand resistance, uh, 10,000 ohms to 50,000 ohms. Or we could say that's 10K to 50K ohms. So the current that flows through your body is really going to depend on the voltage and how good a connection you get, and what your current body resistance is, which is mostly related to your skin resistance. If your skin is very dry, your resistance will be higher towards the 50,000 ohm. If you've been sweating, it'll be lower. And you could even be lower than that if you're very wet. You could be 5K or even less, 5,000 ohms or less. Anyway, we're talking now about resistance from the right hand to the left hand. Resistance from your single hand through your feet and shoes to the floor is almost certainly going to be higher. This is one of the reasons you might have heard people say, if you're working on a live circuit, keep one hand in your pocket. It's a good rule, but it doesn't save everything. It's not the end-all rule. Really, whenever possible, you want to work on a circuit with it shut off. But certain things, such as voltage readings, are virtually impossible to take with power off. Now we call let-go current, And when you go above that level, you can get frozen on. You can't, your muscles will contract and you don't have enough control of them to let go. And that range is in the 6 to 9 milliamp range, 6 milliamp to 9 milliamp range, maybe even as high as 10 milliamps, depending on the individual. So ideally, you don't want to be shocked, but you'd like to have any shock to be less than 6 milliamps so you can let go. Anything above 6 milliamps on up to 10, and as you go higher and higher, your ability to let go of what's shocking you becomes less and less, and probably at 10, 15, you're not going to be able to let go. You're going to be froze on. So hopefully something will keep you, someone will help you out, or some power will be shut off or something before you become seriously injured if you're ever shocked at that level. Let's just say that you get across the circuit in such a way that your resistance happens to be 20,000 ohms. Well, at 20,000 ohms, then we're going to use our voltage equals current times resistance. That 9 milliamps, which was kind of near the upper threshold of what we talked about for ability to let go, we'll put the 9 milliamps here, times 20,000 ohms, and 9 of course just is 0.milliamps, 0.9 thousandths of an amp, times 20,000 ohms. 9 thousandths times 20 thousandths, that's a voltage of 180 volts. So if your resistance that you got connected across the circuit was such that it was 20,000 ohms, if you were anywhere at 180 volts or so, you got a very good chance of getting froze on, being unable to let go. But let's just say worst case, or near worst case, that you're wet and sweaty and stand in a puddle, and maybe your resistance your body resistance happens to be 5,000 ohms. And let's just say that maybe you're as low as that 6 milliamps is the let go threshold for you. 6 milliamps times 5,000 ohms, you have a lower, in this example we got a lower resistance, and we're also choosing more the bottom range if you're the person, a smaller person or something that gets locked on a lower current. Well, let's do this 6 milliamps as amp, 0.006 amps. And we're going to multiply that times 5,000 ohms. 5,000 ohms. Then it might take as little as 30 volts to cause you to not be able to let go. So, in most cases, shock levels up here are probably pretty dangerous, but some cases, shock levels as low as 30 volts can be very dangerous. If you're locked down there with the 6 milliamps and you can't get away, it could eventually cause serious damage, maybe even kill you. Now, let's look at this here example that we had here. 0.9 amps, 0.09 amps times 180 volts. Let's use our power form. Power equals current times voltage. So the power involved here, so let's use our current, 0.09, times the 180 volts that we calculated. Well, that calculates out to about 1.62 watts. So you do not need a really high power source to cause serious damage to a person. 180 volts at 9 milliamps, 20,000 ohms. Yeah, that can be supplied by a power supply that only produces 1.62 watts. That's not a large, high-powered power supply, even though it does have a fairly high voltage output. Let's look at this one here. Your wet, your resistance is down to 5,000 ohms. You're one of the people that can get locked on at 0.06 amps, 30 volts. We're going to use the same power equals current times voltage. Our current was 0.006 amps. Our voltage was 30 volts. Let's see how many watts that would be. See, that's only 0.18 watts, or less than 1/4 of a watt. So in your worst case situation, maybe you had a low resistance, you're standing in the rain, you're all wet, you're one of the people that gets froze on a little bit lower amount of current. A 1/4 watt power supply, that is not a big supply. I mean, basically a couple of car batteries in series could easily produce that. Probably a single car battery, probably not very likely, but maybe on a golf cart where maybe you got enough batteries to make 48 volts or so in series, maybe even a little more than that. I think I've seen 48 volt golf carts. You stand in the rain in the golf course, don't play with that battery. Best if you have trouble with that golf cart, tow it back to the clubhouse and make sure somebody is dry working on it. So electric shock can be quite dangerous, and it varies a lot on what your resistance is and what your threshold of shock. And this is why high-powered radio transmitters are very dangerous. They may not take much current ability to run the output of a say a 500 watt amateur radio transmitter, but you might have 1,000 or 2,000 volts there. You ain't going to have enough resistance. Let's see if you got 1,000 volts. And we're looking for that 6 milliamps, 0.06 milliamps. Well, which is 0.6 milliamps is 0.06 amps. Resistance equals voltage over current. So we're going to go 1,000 volts over 0.006 amps. The 160,000 ohms a body resistance of 160,000 ohms will still pass enough current through you to cause you to be able to possibly be locked onto that thing. And typically your body resistance is less than that, and it ain't uncommon to see voltages higher than that. But what usually is likely to happen, let's say you're at the 50,000, you're dry and you've got a 50,000 ohm body resistance. 1,000 volts, we want to find the current. 1,000 volts divided by 50,000 ohms, that's basically 1 over 50, cancel off these thousands on both sides. That equals 0.02 amps, or 20 milliamps, which 20 milliamps is a lethal level of shock. So you're very likely, can very easily be electrocuted and killed by a 1,000 volt supply that is supplying the power output section of a tube type amateur radio transmitter, say. So when you're working with voltage like that, you want to be really, really, really careful. And if you have to take a voltage reading, it's better to turn the thing off, connect your voltmeter, back away to a safe spot, turn it back on and read the voltage, and then turn it back off before you mess around with it anymore. Now we're going to talk a little bit about what can go wrong with resistors. Basically, resistors can open or they can short. We'll suppose we have a circuit and we have 12 volts supplied to this circuit, and we have 4 ohms, and we do the calculation, 12 divided by 4, we have 3 amps. And that's traveling this way from negative to positive. This is electron current flow. All's good and happy. Suppose that this resistor burns open. What happens? Now, current equals voltage over resistance. So we still have the 12 volts, but now we have an open which amounts to an infinite ohms. And this is the symbol for infinity here, kind of like a little figure 8 on the side, which when you divide infinity into any number, it really just can't go into there. You end up with 0 amps. So when the circuit opens, our current goes from the expected 3 amps to 0 amps. And whatever's in that circuit's going to quit operating. Another kind of failure, a resistor not only can go open, it can go to a higher value too. We'll go back to our original 4 ohms, 3 amps, 4 ohms. Suppose that resistor over time went from 4 ohms to 12 ohms. Now our current is 12 volts divided by 12 ohms, and we end up with, instead of the 3 amps we originally have 1 amp. So this lesser current can throw all kinds of things off in your electric circuit. Biases can be wrong, transistors can be turned off, etc. Pretty much, if that resistor changes from 4 to 12, that's basically a 300% change. This circuit's very unlikely to work. And that's what we call open. So I'm going to write open, broken connection. Now say we had the same circuit rolling along happy at 3 amps. Now resistors, being the material they're made of, they're not really going to likely to go to 0 ohms, or even likely to get much less than the original value. But say a wire gets a bare spot in it, it can cause a path around that resistor. In that path, we're going to call that a short circuit. So what happens when that happens? Instead of 4 ohms, we have basically 0 ohms. And we'll go back to our original I equals V over R, voltage divided by resistance. Our voltage is still 12 volts. And our resistance is now 0. Well, 0 can go into 12 an infinite number of times, so we end up, on paper anyway, we have what looks like infinite amps. Well, the power supply can't supply infinite amps. So what's going to happen is that power supply is going to be drugged down to some voltage that's a low enough voltage that it balances out a lesser current. This 0 ohms is probably not quite actually 0. Maybe it's 100th of an ohm, 0.01 ohms, which is pretty low compared to 12, or compared to 4 ohms. That's 1/400th of it. So our current would want to go up 400%, which would be like 1200 amps. It can't do that, so maybe we drag the voltage down to, well, we drag the voltage down to 0.1 volts, because that voltage supply can't supply an infinite. Now we end up with maybe, maybe 10 amps. Or maybe this voltage only goes down to 0.3 volts. And we end up with maybe 30 amps, which is still way above the original 3 amps are supposed to be there. And that can cause damage. So usually, or commonly anyway, we will see in this circuit a fuse. And maybe this is a 5 amp fuse. So long before we get to this 30 amps, we will blow the fuse will open, and we will no longer have any current flow. Current flow will go to 0. And that will protect our circuit. So in general, resistors can increase in value or open. Now they don't usually go down because they're made of resistant materials. It's pretty hard to make it lesser value, but some other alternate path can cause what's called a short around that thing and cause the current to go up, which usually most circuits have a fuse to protect them, and the fuse will blow, and that will be the end of your circuit operation until you get it repaired. Go in there, find the short, remove it, put a new fuse, turn it on, see if it works. And if it ain't working, continue on. Anyway, that'll probably be enough for today. Be sure to like and subscribe so you get notifications and such. And until the next time, keep on learning.